Good morning, everybody. Welcome back. This time actually from my actual office. What a change. So this week I actually would like to talk about the functional approach to interprocedural data flow analysis. And in the previous weeks we have already covered everything that you can see here, which was basically preparing us for covering inter-procedural data flow analysis. So particularly we covered all the intra-procedural ways that are relevant. Then we also talked about call graph and pointer construction and how to bring that to the inter-procedural level. And then we also already covered general interprocedural flow-sensitive analysis and the problem of context sensitivity that you get there. And we already discussed the call strings approach. And the functional approach that we will cover today is really quite a different way of thinking of context-sensitive analysis. And that's what I want to bring across today. If we briefly recap the so-called call strings approach, then you may remember that it's somewhat similar to the traditional monotone framework in the sense that we propagate through the interprocedural control flow graph simple data flow facts. And in fact, within procedures, we have pretty much of a normal propagation. But the main difference to this traditional monotone framework was that this time the data flow values, they're annotated with call stacks, and we discussed that these call stacks, they need to be bounded. Then at calls, we're basically extending the stack. So we're adding calling context information to it. And then at returns, we are popping the caller off the stack. And in particular, and that's really the most important point, we return this data flow fact only to the rightful caller, right? That's exactly what this stack is all about. Then also we talked about bounding or k-limiting because we need to avoid infinite recursion and infinite growth through recursion. So we need to basically bound the abstract domain. Make it finite, and that we do by limiting the call stack to a finite size k, so that we then in the end have a so-called k context sensitive approach. And we discussed that there are different ways in which this k can be limited, but in practice it's typically very low, right? So it's a very small number in the order of, I don't know, 1 to 3 or something like this. So typically you won't see any larger case than that. So today, instead, we want to talk about the functional approach, which is a very different way of thinking about context sensitivity. So here the assumption is that at a call, so when we process a method call during the analysis of some certain procedure, we assume that we already knew what the callee's effect on the abstraction would actually be. Okay, so we assume that we have already somehow pre-computed what is the effect of the method that we are calling there. And under that assumption, then when analyzing the call within the caller, we can simply plug in a summary of the callee's effect. Okay? And if you can make that assumption, then what's interesting about this is that the caller analysis is then actually simply an intra-procedural analysis, right? So if for every callee in your current procedure, you know what the effects are, and you can simply model them as a summary function, basically then as a simple flow function, then the whole problem of analyzing the caller simply reduces to an intra-procedural analysis. But of course, this does require these summary functions for the callee methods. Okay, so just to show you that again in terms of some pictures here. So in the traditional monotone framework, if this is the caller and this is the callee, then we would basically analyze to the caller until here, getting some data flow fact x that is forwarded here. Then we would compute some flow function here. So at this point, we would have fr of x or x prime, which is then propagated here, and we would continue computation with that, right? But now in the functional approach, it rather looks like this. So we assume that, first of all, right now, let's assume there's some magic involved, right? That pre-computes this summary function here. So we already are given fr. And because we know fr, we can simply apply fr directly to x here. We can simply plug that in. We immediately get x prime. And then we can actually propagate this information here. Okay. So what's nice about this is you can imagine that this procedure R here, it can be called thousands of times at thousands of different places in your program, right? And if I've pre-computed this fr and I can simply apply it at every call site of R, then the analysis will be accelerated quite a bit, right? Because you can simply reapply the summary function in every other calling context. And that's quite different from the call strings approach. So if you remember, at the end of the previous lecture, I already showed you this example here, where we were basically assuming that we have a taint analysis that is tracking all of these three different sources here. So all of these three values, h.f, i.f, and j.f, they're actually all containing tainted data that needs to be tracked through the program, all right? And now the problem was that if we have the first calling context for foo here, so C1, the first call site, then this will cause, using the call strings approach, an analysis of foo where all the data flow facts here, in particular a.f, which is tainted, that will be tagged with this calling context string C1, okay? And then we conduct the analysis and we return to C1. But then we will be doing this over and over again, right? So here, because I is tainted as well, or I.f is actually, then we will be conducting the same analysis as before, simply with a different calling context, now for C2, and then again for C3. So in the end, you have a repeated analysis of this calling procedure, which is all identical in every case except for that other calling context. And what we are actually looking for is an approach that doesn't waste all this work, right? We want an approach that computes sort of the left-hand side of this tuple once, right? So that tells us once that if a.f is tainted at the beginning, then b.g will be tainted in the end, irrespective of the calling context, or at least for a large number of different calling contexts, let's say, right? So we want to be able to somehow quantify over these calling contexts to say, I don't care whether it's C1 or C2 or C3, I just care about that it is a calling context that taints a.f. And if that is the case, then I know that b.g will be tainted in the end. And the functional approach will give you exactly that. So to slowly transition you into this other way of thinking, let's show you this other example here. So let's assume we are having a program here that is doing some simple integer arithmetic, right? So it's simply computing a couple of numbers here. And now we want to think about how to do this in the functional approach. So at the beginning, let's say we don't know anything about any constants, right? So our analysis information here, it's simply empty. Then we learn that x actually has the value 1 and that y actually has the value 2, okay? Now we would like to analyze that procedure call here, but in order to know what value z is being assigned, we actually need to know what is the effect of foo here, okay? And like I said, in the functional approach, we assume that somehow magically there's a summary function given. But the way this actually works is that the first time a call is encountered to a procedure such as foo, which has not been summarized yet, that summary is actually being created. Okay, so let's focus on this callee procedure foo first to see how one could compute such a summary. So the summarized effect of this procedure, what would that be? If we take a look at that procedure, well, what is it doing? It's first of all incrementing the value a. So a becomes a plus 1, you could say. And then it's taking that updated value of a and it's adding b to it. All right? So you could say that the summarized effect of that procedure is that the return value that is being returned from that procedure, it's a plus b plus 1, right? Due to that incrementation that we have here. Actually, if you're really tedious about this, then you would have to say that the summary is even more broad than this, because it would also need to contain some information about a, because the value of a is changed as well, right? We don't just update or compute a return value, we also update the value of a. So a at the end is a at the beginning plus 1. Okay, so a full summary of that procedure would actually look like this. It would also contain a value of a. Although having said that, the summaries that the functional approach will typically store, they will not contain any information about variables such as a. Why is that? Well, if you look at a, it's a parameter, all right, but it's actually a parameter that is akin to a local variable because it's only visible within foo, right? The name a has no meaning to any caller of foo. It's not in scope, it's only in scope within that procedure. So yes, this is a correct partial summary for this function foo, but it has no bearing on any caller, so there's no need to store it. Whereas the return value, obviously, it is important to the caller, right? So the summaries basically are being reduced to only information that matters to the caller. Now, if we assume that we have computed such a summary, then we can go about it as follows, right? So we start our computation as we have done before, and now we want to process this call to foo, and we assume that we already have this summary. Now, you will notice something if you look at the summary. This is talking about a and b and some return value, all of which don't really have a meaning in this scope here, right? So in this calling context, we have no variable a and b. We also have no variable called red. We do have one called z, but it's a different name, right? So the problem is here that yes, we do have a summary, but it's still what we call a callee side summary, right? So it's a summary expressed in terms of the variable names that the callee knows. And in order to be able to use that, in this particular calling context, it needs to be adapted to that context. And that can be done relatively simply. In essence, in the implementation of these analysis frameworks, it's done through two replacement functions. So first of all, here we will have a call function, a call flow function that replaces x by a and y by b, or depending on how you look at it, you can also see it the other way around. And then we have a function that replaces z by the return value. And if you apply these functions to the summary function here, such as that, then you will basically get a reduced summary function, a caller side summary function that is, due to these two replacements here, made specific to that particular call side, right? So this is really where we take calling context into account. Yeah, then you have this caller side summary, and this all of a sudden it makes a lot of sense, right? So we know y, we know x, and we know what z is, and now we can use that summary to actually plug it in as an effect of this procedure call here. So we will apply that here, and now we know that actually x and y, they're not updated because the summary says nothing about x and y. But we also know that z should be getting the value 4 because we need to add 1 and 2 together plus 1, right? Which gives the value 4, which is exactly what we have here. So this is one example to show you how such a summary computation would actually work. But I want to show you how to compute these summary functions in a more general setting. So for now, let us assume that we're doing a forward analysis, but for the backward analysis, it actually works the very same way. And assume we have some procedure R, and it has a control flow graph that looks like this. So this is an intra-procedural control flow graph of procedure R. And F1 through F4, there are flow functions for these individual statement nodes that we have here. And now we have these functions here that are meant to summarize actually the effect of the procedure. And importantly, this is the effect that summarizes the entire control flow and data flow from the beginning of the procedure through the particular program point to which this function is annotated. So if I look at this function here at this location U7, then it's basically saying it's summarizing the entire effect from here to there. Okay. And what's interesting now is that the summary computation, it can happen incrementally. So that means at the beginning, we are computing a summary function that brings us from here to there. So to the same code location. So this is sort of some bootstrapping. We are it's like a base case for an induction, you could say, right? And what is the data flow function from here to here? Well, it's the identity function, right? So it's a simple identity function that doesn't compute anything really. And then we are extending this particular summary function that we already have to include a summary also of this first node, or you could also say this first flow function that we have here. And well, this is simply identity composed with this flow function, which is again the flow function itself, right? So here we simply use F1. And this is then also propagated to here and to there, because here, there are no effects. And now we are extending this. So if we look at the right-hand side branch, now we are adding the effect of this flow function F3. And what's important now is that we are not actually computing yet this effect. We are simply accumulating this effect. So that means the flow function computation, it's not actually being conducted here, it's rather being collected symbolically. So that means we are not evaluating F1 and we are not evaluating F3, but we are rather constructing an expression that tells us that whenever we want to apply that particular summary function, we need then to actually compute F1 followed by F3, right? So here we are storing this function composition. And we do the same on the left-hand side branch. That's actually pretty simple. So you can think of it like, we start with this bootstrap case, then we extend this summary function like I showed you. We extend this further until here, and now we have a summary function, this one here, that brings us from up here to down there. Now something else slightly interesting happens because now we actually have a control flow merge, and ideally here we would also want to merge our data flow information. And so the question is, how do we do that? Well, again, we go about this symbolically, right? So we are not actually executing the merge, but we are simply tracking it, right? So the summary function that we are computing here, it's actually taking the summary function that we have already computed for the right-hand side branch and the one for the left-hand side branch. And it's now again composing them, but this time with a merge operator. So obviously, we assume that we have a merge operator given on the abstract domain that we have for this data flow problem. But this is now sort of a lifted merge operator defined on the flow functions. But typically, it's very easy to define such a lifted merge operator because all that it does is once you apply it, it basically applies the merge to the results that these functions actually compute. And this is again our new partial summary function that brings us up to here. And now we still have to compose that with F4, and that then brings us the final summary function that you see here. Okay, and that's it. So once you have this summary function that goes all the way from the top to all the way at the bottom, that is your final procedure summary. That is a summary that you can use to summarize the entire effects of this entire procedure. And in fact, once you have computed this summary that spans the entire procedure, you can get rid again of all of these intermediate procedure summaries. They are not useful anymore. All that we need is to store this summary that summarizes the entire procedure. Okay. Just to show you that again, for a small example, let's assume again we are having this increment procedure that we had earlier, right, where we increment A and then add B to it. So here our intermediate summary function, it would be bootstrapped with identity like I showed you earlier. And then we would compose the identity function with that effect here, right? So this is the flow function that we have for that particular statement, and we are simply adding its effect to the summary. So that brings us here. And then if we have the summary function that brings us all the way to the bottom, then this is extended as follows. So we still keep the original summary that we have, but now we are adding a summary that is basically computing this effect. So it's telling us that R is effectively A plus B, although not quite. We have to compose that particular flow function with this one. And if you do this, then you basically obtain this flow function here, right? So it's not just A plus B, but A plus B plus 1. And that will then be our final summary function, except that I told you that this part of the summary is typically omitted, right? Because it has no bearing on the caller. So that would typically not be stored as an optimization to the analysis framework. So just to give you an algorithmic description of this, so you can basically say that you have different entry points to different control flow graph nodes n in your procedure that you want to compute. So we saw that there were all these functions at the entry to a node and at the exit to a node. Okay. So this is basically before and after a statement. You can also see this notation that I have here. Okay. And yeah, then this is basically computed as follows. So let's maybe first take a look at the entry case here. So if n is your start node, then we said that you start with your identity function. If it's not the start node, then you simply take all the flow functions that you have already computed at the exit of the predecessor nodes, right? So you iterate over all the predecessor nodes and you take the exit flow function, summary functions, excuse me, and then you're merging over them, okay? That's in order to implement this merge semantics that we need. And then if we want to compute the summary function for an exit, then we basically need to take into account the flow function of the current statement, which is this function here. Okay. So if n calls procedure S and U is actually the exit, so the exit function of the end statement of S. So this is basically a procedure summary for a call. Okay, then we are plugging this procedure summary for the call in here, and we're taking the summary function that we have already computed for the entry of the current node, and we are extending that summary function with this call effect. And if it's not a call statement, well, then we simply take the current flow function of the current statement instead. Okay. And that's all that we need to do. So you can basically compute this as a large fixed point iteration, and then you will get a result. Okay. Now, you can try at home to compute such a summary for this particular function here, which computes the greatest common denominator. And you can take a look at how this works. And this, I would say it can take a couple of minutes. So if you want to do this in your own time, I encourage you to stop the video now and maybe take 5 minutes or so to take a look at how you could compute a summary function using this procedure that I showed you for this particular method here. And then we'll get back and see what the result might look like. Okay, I hope you didn't look into this for like half an hour or so, because this was actually a bit of a trick question. When you try to apply that algorithm to this particular procedure, you will see that it's not quite that straightforward. So let's start by the following. So first of all, these expressions here that are part of the conditionals, we don't really care about it in our static data flow analysis. So like I told you earlier, there are some particular static analysis that do look at these conditionals, but typically we are not interested in them and we simply abstract away from them. So the control flow graph that we look at, it actually looks like this. And then if we first compute a summary from the start of the procedure to here, to just after this node actually, then this is what our summary could look like, right? So x equals x minus y. The thing is now, well, we can go around this branch, right, and we can iterate through this loop. And if we do this again, then we will actually get an expression that looks like this, right? X is x minus y minus y. And as you can obviously see, this can be iterated forever and forever, right? So there is a problem with loops, and that needs to be dealt with somehow. And how you deal with such loops and what can be done about it, I will tell you in the next video. So please bear with me. I'll be with you whenever you start the next video. Thank you. Bye-bye.